Hi, everybody. My name is Mike Coward. I'm the part of the encoding team here at Facebook. Really appreciate you all coming out today. It's a lot of fun to get to talk about the work that we're doing, share some of the lessons we've learned, and actually learn from all of you about the things that you're doing. You know, the mission of the video encoding team is actually pretty simple at Facebook. Our goal is to give people the best experience, the best viewing experience for the most people. Facebook has 500 million people that watch videos every day. So we're really sensitive to, I think, the global reach that we have as Facebook, and how can we make that experience better around the world. You know, this is a lofty mission. At the end of the day, it actually comes down mostly to how small can we make these video files. The smaller they are, the faster they play back, the less egress we use, the less mobile data we use. So in a way, the job is actually pretty simple. Preserve quality and push the files to be pretty small. One question we get a lot is, well, why not just use a new codec? There's new standards, there's a lot of proprietary codecs that companies have developed and come pitch us all the time. This is the biggest reason. We have thousands of different devices accessing Facebook every day. There's dozens of versions of the operating system, dozens of versions of drivers. And what we found is that pushing new software down to the phones is really difficult. For most of our views are on mobile devices, so we want to take advantage of the hardware decode. And for that reason today, really all of our video delivery is H.264. It's hardware decode, it's battery efficient, it works on all devices. So we'll certainly explore others in the future, but this is our solution today. Encoding actually began with a question. So I was talking to a colleague about this shiny new distributed encoder that we built. And I told her, hey, we can process videos at 10 times faster, 100 times faster. And she looked at me and said, well, what if I don't care? What if I give you 100 times more CPU? How small can you make that file? What can you do for me? This is what I care about. So we went off in a dark room, and we cried. And then we started to think about it. And in particular, the first thing that came to mind was, 10 years ago, we used to hand tune the settings for every video. We would look at a video, we would watch it carefully on that color calibrated monitor, and we would find the best settings for that video that preserved the quality and made the file as small as possible. So why don't we do that today? Right, today we have one setting, we use it for all the videos. Here's the reason. Here's the videos we received this second. Here's the videos we received this second. The scale here at Facebook, we can't hand tune them, obviously. Even the popular videos, right? 1% of the videos, if we wanted to tune those, that's thousands of videos a day. It's not going to happen. But this gave us a clue. What if we could get the same benefits of that hand-tuned experience for thousands of videos a day, millions of videos a day? What would that look like? What would that feel like? I think we all know that encoders today, there's lots of parameters you can play with. Sometimes it makes the video better, sometimes it makes it worse, but there's a lot of things you can do. This is great. This is fun as an engineer. If you're trying to pick the single best setting, that's really hard. But if you want to pick the best setting for a single video, that's kind of fun. So hey, she gave us 100 times more CPU. I've got a great idea. Let's just pick 100 settings at random. It's almost certainly going to be better than it was. Let's pick the smallest one, and we're done. So go have a beer. Well, actually, a couple of problems, as you can imagine. The first one's actually kind of subtle, and that is when you change the settings of a video encoder, you change the file size, of course, but you also change the output quality. So if you do it naively, and you just pick 100 settings at random, you're going to pick the one with the worst video quality. Not very exciting. So I'm not going to talk a lot about this point. This is a subtle point. But if you're going to do a technique like this, you do need to go correct for quality through the entire pipeline. The bigger problem is actually just the number of options we're talking about. I talked about encoders have dozens of options, right? There's ones that are continuous, where you adjust the strength of how bits are allocated and the quantization parameters. There's discrete parameters, some of the deblocking parameters, or things that you can turn on and off. So even if you constrain it to 8 parameters, and then you go say, okay, great, I'm going to choose 8 parameters, I'm going to choose 100 settings at random. The chance you're going to pick the best one is a 1 in 15 billion, which, as we all know from last week, is worse than the chance of winning the lottery. And since you're all here, I'm guessing none of us won the lottery. So at Facebook, pretty much every problem, our hammer at Facebook is machine learning. So when we have a problem, when we have something fuzzy, we throw some machine learning at it. There's lots of styles of machine learning, SVMs and neural networks and ones I don't even remember. But the one that we chose is neural networks. And the reason we did that is really 2 reasons. The first is neural networks do particularly well when you have inputs and outputs, and the relationship between those is not very obvious. Neural networks are really good at teasing out the subtle things that you're not going to see yourself. The second time you want to use a neural network is when you have a lot of data. You have a big training set. Fortunately at Facebook, we get a lot of videos, so it's pretty easy to put together a big training set. For those of you, since you're video engineers and this is not a data conference, let me give you the 1-minute reminder of how a neural network works. You have a set of inputs, you have a set of outputs. In the middle, you have a set of hidden nodes that are connected between the inputs and the outputs. If we dive in and look at the internals of one of those nodes, every node has a weight for all the inputs that are coming in. The only thing the neural network does is it sums up all the input signals with those weights. It spits it out. It applies a weight on each of the outputs. And then your output node sums it all up. So kind of simple. It's actually, this part is really, really easy. Like actually running the neural network is really, really simple. The hard part is training. The first thing you have to think through if you're going to use a neural network is what's my input and what's my output? What are these values? How am I going to map things in and out? There's a couple options. One is you can just shove every pixel, shove the raw value into the neural network, build a neural network with 20 or 30 million inputs, and you're set. And that's actually what a lot of people do for image classification, to figure out if it's a dog or golf. The second thing you can try to do is you can use some external system and extract semantic features. Is it golf? Is it a rocket ship? Is it outer space? And you can feed those parameters into your neural network. But actually, that just moves the problem out. Semantic extraction is a pretty hard problem. So the third thing you can do is you can extract statistics about the video. How much motion is there? What's the color space? What's the distribution of various internal parameters? As you can probably guess, this is the one that we chose. And we call these statistics the fingerprint. And in particular, we extract 116 features about the video that we then pass through our system. Your second decision is the outputs. You have to decide what those values coming out of the neural network actually are. One option is each output node, each output of the neural network gives you one parameter for your FFmpeg command line. One of those might be deblocking, one of those might be quantization strength. In that case, you take all the outputs and you take the sum of all those outputs, and that's your FFmpeg command line. There's another approach where every output represents a set of parameters, so a particular command line that you like. And really what you can do here is you pick the node that is firing the most strongly, that has the strongest signal. And that's the one, those are the parameters you use. So in this approach, you only use the output of a single node, but the neural network tells you which one to use. As you might be able to guess, that's the one we chose for a bunch of reasons I'd love to talk about. So let me take you through the 3 steps we're going to talk about in the next few minutes. The first is you generate a training set. You then actually have to train your model. You have to build your neural network model. Then you have to use it. And it's important to note that the two blocks on the left, you do this one time. So this is building the model. And then using the model, you do that on every video. So we'll make that distinction. So obviously, you don't care much about how long the stuff on the left takes. You care a lot about how much using the model takes. The training set was pretty easy. We picked a few thousand videos that were popular and that represented the kind of content that we get here at Facebook. We then picked several thousand options that represent our best guess as to options that would do well here. And then we encoded every video with every set of options. So as you can imagine, this is when it's really helpful to be Facebook. This is our data center in Sweden. We kept this pretty busy for a week using off-peak hours in Sweden. So we had thousands of videos, thousands of options You can do the math on how long that would take. For every video, then we went and we extracted that fingerprint that I talked about before. So that was the characteristics of the video. And then we dropped that all into a database. So we've got a massive database here that says, for these millions of encodes that we've run, what's the size, what's the quality, how long did it take, and then what's the fingerprint. So that becomes our training set. That's the data that we use to train our model. The next step is actually to build the model. So actually build it, create the neural network. So you take all that database. We used an internal tool here called FB Learner. This looks really easy because it's just one box on my slides. Really, really hard. So I credit all the AI researchers here. They've made it amazingly easy. But this is essentially doing the training, again, hundreds and thousands of hours to actually train that model against our training set. And really what that spit out for us is this neural network model that we can then use for every video. So using the model. So this is what we do now for every video. We bring it's actually pretty obvious, right? We bring the video in, we generate a fingerprint, we ask our trusty neural network what the output should be, or what the best settings will be for that video. We encode the video that way, and we have an output. We did this. We actually got pretty good results, and we're just about to roll this out. And then we actually had a bright idea. We figured out a way to make it better. Every video has different scenes in it. And it might have a title sequence, an explosion, some romance, the credits. And those scenes are as different from each other as any two videos. So using that thought, what if we could apply this technique and do it scene by scene? So this is really akin to the original days of hand-tuning that video, go frame by frame, and adjust the settings to make that video as strong or as good as you can. And this is what we call per-scene analysis. So again, we take that video. This time we segment the video. So we break it into a set of pieces, that basically a set of scenes. Every scene we pass up to our fingerprint generator to generate a set of fingerprints. We can pass those into the model, get settings back from the model, run all those settings together, have all the final segments, put them all together, and declare victory. If you've been paying attention, this is pretty similar to the distributed encoder that she just talked about. And so obviously these two work together very well, right? You segment the video, you figure out these parameters. So a lot of common ground here. Who wants to know the results? Yeah, awesome. The first result is really important to highlight. This is a bit stream we can play anywhere. So it's compatible with our existing players, our existing delivery. It made it really, really easy to roll this out. It's pretty expensive, 7 to 20 times more CPU. The good news is that it helps. The good news is that it works. 20% smaller videos. So compared to kind of the state-of-the-art command line options that you're used to, we're seeing 20% improvement with this. Obviously, you're not going to believe me, because it's hard to compare sizes and qualities, but I encourage you to try it. So what would this look like in production? As I said, it is a relatively heavy encode, so it's something that we probably don't want to do everywhere, or we would need some more data centers in Sweden. The good news is that Facebook video follows a very typical power law distribution. And what this means is that 1% of the videos that we host here at Facebook get 85, 86% of the views. And if we push the encoding across 10%, then we've covered almost every video view that people are watching. So for a technique like this, we can actually deploy it at scale and get a lot of the benefits, even with that CPU penalty that we pay for encoding. So what's next? Hopefully I've given you a good primer on where we're at. Today we've used the technique on H.264. It's done well. This technique obviously scales nicely into future codecs, so we're exploring that. There is just a lot of interesting work to do on the neural network to continue to optimize it. We saw just sort of 5% improvements as we went from our first generation to our second generation. So there's a lot of interesting analysis, a lot of interesting work. But really what we're proud of is bringing the results of hand-tuned encoding back to video at scale. So with that, I'd like to thank you and pass it off. Lauren.